Hello student, welcome back. This is Vasanth from Canara Engineering College. In this session we'll see flip-flop excitation table. Like in synthesis or design problem, excitation tables are very useful. Excitation table of a flip-flop is looking at its truth table in the reverse way. You can see here first in this truth table or in this truth table or transition table, output comes first, then next input comes. So as mentioned here, excitation table of flip-flop is looking at its truth table in reverse way. Here, flip-flop output is presented as a dependent function of a transition from Q to Qn plus 1 and comes later in the table. That is, input comes later in the table. Here you can see. So now, how to represent this excitation table for SR flip-flop, SR, JK and DT. So we have to see the cases when the last state is Q and next state is Qn plus 1 for combination 0, 0, 0, 1, 1, 0, 1, 1. Now you see when the flip-flop is in 0 state and it wants to move to the next state 0 state, then what should be the combination of SR? For that I will take you to the previous slide. Here you can see when the flip-flop is in 0 state, and to move to next state also 0, to move to 0, then here you see combination of SR is 0, 0, 0, 1. That means S will remain same, but R will vary. So R can be X, the value of X can be either 0 or 1. To move from 0 to 0 state only. So that is represented here. Here S is 0 and R is X. To move from 0 to 1, what is the value of S and R? You can see here to move from 0 to 1, 0 to 1, the value 0 to 1. So let me show this one, 0 to 1. So year to year, the value of SR is 1, 0. So you can see here value of SR is 1, 0. To move from 1 to 0, 1 to 0, 1 to 0, the value of SR should be 0, 1. So you can see here 0, 1. And to move from 1 to 1, that is present state is 1, next state is 1. So 1 to 1, you see here 1 to 1, to move from this state to this state, present state is 1, next state is 1. Here you can see the value of S and R. S and R. R remains 0, but S will vary between 0 and 1. So I can take the value of S is as X. The X value can be 0 and 1. 0 or 1. So here you see that is X and 0. Similarly in JK, to move from 0 to 0, it is 0x only. 0 to 1, we will go to this slide. 0 to 1, here you can see to move from 0 to 1, this is the value of JK. That means J remains 1, K will take value 0 or 1. So I will write 1x. So that is represented here 1x. Similarly, to move from 1 to 0, it is x1, and to move from 1 to 1, we will see 1 to 1 case. 1 to 1, that is to move from 1 to 1 year to year, you see J is taking value 0 and 1, K is 0, that means x0. So you can see here x0. Similarly, we have to see now D and T. So in case of to move from 0 to 0, D should be 0. To move from 0 to 1, D should be 1. To move from 1 to 0, D should be 0. To move from 1 to 1, D should be 1. Similarly, T. So this is called as a flip-flop excitation table. It's very necessary in the synthesis design. So student, the next topic is flip-flops with the additional input. Flip-flops often have additional input which can be used to set the flip-flops to initial state independent of the clock. In the diagram you can see here, we have D type of flip-flop. Normally this kind of D type flip-flop contains a D input clock signal, output and complement of the output, Q or Q bar. Other than that, we have two more signals, that is called preset and clear. So why preset is used? By using preset you can set the flip-flop. By using clear, you can clear the flip-flop irrespective of a clock signal. That means you can set the flip-flop asynchronously, or you can clear the flip-flops asynchronously. So here you have to make a note of one more point here. Both preset and clear are called as active low signal. Active low signal means the signal which some negative value causes some effect on the flip-flop here. Negative value causes some effects on the flip-flop. You can see the small circle, that is the inversion symbol on this input indicate that logic 0 rather than logic 1. This is called as a active low signal. It is required to set or reset flip-flop here. Preset and clear signals are used to set or reset flip-flop. So this is the truth table related to preset and clear. So one of the application of SR flip-flop is switch contact bound circuit. So what do you mean by switch contact bound circuit? So diagram shows the switch contact bound circuit. Here you can see we are using a switch which is connected to voltage source, and right now here the switch is open. When the switch is open, the voltage at point A is 5 volt, this one. When switch is closed, then output moves to 0. But here the problem is when the switch is closed, because of some mechanical component inside the switches, it bounces back to 0 and 1 till it achieves or reaches its stable state 0. That is called as bouncing. So we can use SR flip-flop in order to avoid the bouncing effect of the switch. The bouncing effect of the switch. You can see the debouncing circuit by using SR flip-flop. Actually, this mechanical arm, when it is moved from one stable state to other stable state, that is when this mechanical arm is moved from one stable state to other stable position, the arm bounces like hardball bounces. The solution to this one is debouncing circuit. Debouncing circuit means we are using SR flip-flop along with this this switch. So when you use SR flip-flop along with this switch, then output remains same irrespective of this bouncing. The output of the flip-flop remains same. Here you can see the flip-flop. See, output changes here. Sorry, when like the switch position bounces from low to high, but output remains same. That is, here you can see output remains same irrespective of that one. That is the property of the SR flip-flop.